Hello, everyone. Welcome to my project presentation, and the topic is strategies for low temperature operation of batteries. So, lithium ion batteries are everywhere, from our phones and laptops to electric vehicles and stationary energy storage systems. They're popular because they pack a lot of energy, they're lightweight, and they last. However, their Achilles heel is extreme temperatures. When it gets really cold, the performance drops sharply, and this is critical for applications like defense, aerospace, transportation, and energy storage, where reliability is extremely important. Now, the go to solution today is to heat the battery so that it stays within an optimal temperature range. But heating drains energy, and it does not scale well for big systems like grid storage or fleets of vehicles. The agenda today is we'll discuss the motivation, the science behind the problem. We'll look at the materials individually, cathode, anode, electrolytes, and then the dominant technique to overcome this limitation, which is external preheating strategies. Then I also propose mixed chemistry batteries and hydrogen energy storage system. Coming to the motivation part, so although the optimal lithium ion battery operating temperature is between 15 to 35 degrees Celsius, real world climates from blazing summers to freezing winters push batteries to their limits. This is especially true in regions like North America and Canada, where temperatures often drop to minus 20 degrees Celsius and even below, causing serious battery anxiety. So below 0 degrees Celsius, chemical reactions slow down, internal resistance increase, leading to reduced range. So it reduces overall efficiency and range, and we may lose up to 40% of battery's rated capacity. It results in slow charging, so charging rates can drop to zero point zero 0.05 C to zero point 0.1 C as opposed to 2 C to 3 C in normal scenario, extending the charging times to more than 2 hours. It leads to shortened battery life. So at low temperatures, lithium ions deposit on the anode surface instead of intercalating into the anode, leading to a phenomena called lithium plating and dendrite formation on the anode side, causing permanent capacity loss and can lead to safety hazards. And it is a failure mode as well. So the inspiration for this topic stemmed from witnessing a colleague's real world experience with their EV during a brutally cold winter day this January of 2025. So the car was parked outside for several hours and it was soaking in the minus 20 degrees Celsius temperature outside. And by the time my colleague reached a supercharger, the battery was down to about 20% SOC. When plugged in, the EV immediately entered a battery preheating phase, which is actually required to bring the battery up to a safe temperature before it can actually accept charging. And for the next 45 minutes, the car drew no power for charging, and the SOC remained flat at 20%, and all the energy went into just preheating the battery. Once charging finally began, the expectations of a high speed charging was quickly gone because despite being connected to a 250 kilowatt capable charger, the vehicle initially drew just 3 kilowatt, barely enough to make a difference. Whereas in warmer climates like Los Angeles, where temperatures hover around 20 to 25 degrees Celsius, charging at low SOC typically pulls in 175 to 180 kilowatt right away. But in this extreme cold weather, even after preheating, the battery wasn't warm enough to accept high charge rates. And it wasn't until the battery reached about 30% SOC that charging speed improved to around 20 kilowatt. And then eventually it climbed to 40 kilowatt at 50% SOC. By 60%, it hovered around 44 kilowatt. Still far, far below what would have been expected in a warmer condition. So the entire process dragged on, turning a 30-minute pit stop for fast charging into a 3-hour ordeal. So this underscores a critical limitation that batteries in extreme cold require significant energy and time to precondition. And even then, charging rates remain throttled until the pack warms internally. And this is done by the BMS to protect the batteries. Because unlike gas vehicles where it generates waste heat to offset the ambient cold, EVs rely on active heating systems that drain energy. It is time consuming and it also extends the charging times. So I believe EVs are super cheap right now. I guess the leading model is at 299 per month, 1,000 down for lease. But for anyone without a home charging in Midwest, it is inconvenient. Especially for apartment dwellers relying on outdoor parking, they face this double bind of preconditioning, energy drain, and extended charging stops. And some tips and practical solutions are offered to manage the situation, like they say park the car in a temperature controlled area, or preheat the vehicle while it's still plugged in so the energy is drawn from the grid and not from the battery, or minimize short trips to avoid frequent false start, so the battery to avoid frequent heating up of the battery. Or they say use heating or a steer seat or steering wheel heaters which rely on the which draw power from the auxiliary battery instead of the main HVAC system which draw power from the main battery. So these may lessen the impact, but they do not really address the uh, underlying poor performance issue. So looking at the science behind it, so unlocking high range and fast charging for lithium ion batteries in cold winter is a challenge. And the root of this problem lies in the fundamental battery chemistry and the physical properties of the materials involved, such as the composition and microstructure of the electrodes and electrolytes. So, lithium ion batteries struggle in low temperature due to these factors, like a sluggish lithium ion kinetics at the electrode electrolyte interface, increased resistance from the solid electrolyte interface or SEI layer, and increased viscosity of carbonate based solvents. So, this will raise the lithium ion dissolution energy barrier, um, which will reduce ion mobility through the electrolyte. So, as a result, lithium plating and dendrite formation occur at the anode, compromising both safety and efficiency. So, the current strategies to mitigate these limitations often rely on external thermal management systems such as secondary heating, which will warm the battery from the outside to maintain optimal operating temperature. But this consumes additional energy, increased cost, and system complexity, and l- doesn't address the real root of the issue. So, future advancements are focused on re engineering battery materials and their interfaces. And the key directions include modification of electrodes, modification of SCI interface or SCI interface engineering, development of new anode materials, and novel electrolyte formulations. So, yes, external heating is a helpful solution for now, but the long term path lies in fundamental advances in battery chemistry and material science. Let's look at each of these material issues one by one, starting with the cathode. We'll look at the challenges, modification strategies, and some of the recent research vectors and advancements in each of these frontiers. So, one of the primary challenge in cathode is the low diffusion coefficient of lithium ion and the high charge transfer resistance. And all of these arise from the sluggish electrochemical kinetics. This leads to increased polarization or voltage drop, reducing overall battery performance, and especially at low temperature. So, to improve cathode kinetics and stability, researchers have developed several modification strategies such as surface coating, element doping, and particle engineering. So, let's look at surface coating. So, um, the research has shown that carbon-based coatings, such as those applied to LFP, improve electrical conductivity and facilitate lithium-ion transport. Oxide coatings like lithium borate on layered oxides of NCM significantly decrease charge transfer resistance, and it is often combined with carbon coatings to improve both contact and stability at the electrode electrolyte interface. Metal fluoride coatings such as 2% aluminum on lithium-rich layered oxides have demonstrated increased capacity even at minus 20 degrees Celsius. Conductive polymers such as 2.95% polypyrrole coating on LFP also show similar benefits to carbon, but they offer greater compatibility with the electrolytes. Now, coming to element doping at cathode. So, element doping targets intrinsic material properties. So, core doping with lithium and molybdenum into layered oxides have shown to enhance electronic conductivity and structural stability. Boron doping in carbon modified NMC cathode accelerates kinetics, while trace aluminum on NCM cathode accelerates lithium ion diffusion. Transition metals like titanium, chromium, and cobalt improve capacity and reduce activation barriers. Phosphorus doped LFP or graphite has shown gains in specific capacity and Coulombic efficiency. Coming to the third strategy, so structural and morphological optimization. This further complements the previous strategy. So the idea is to reduce the particle size, and that which will shorten the lithium diffusion pathways, will also increase surface area, and might improve electrode electrolyte contact. So it has shown that high purity LFP outperforms industrial grade counterparts, emphasizing the role of material quality. And innovations like coil shaped LFP or graphene composite cathode with many holes inside which act as chambers for ion transport and intercalation. This will increase surface area, enhance structural stability and diffusion kinetics through this special morphology. So something similar is shown in the picture on the right. So the takeaway is that despite all the progress, challenges persist. So current research prioritizes transport properties or conductivity and stability of the cathode, but it often overlooks the holistic integration of solutions. So, for instance, excessive surface coating risk generating byproducts like iron phosphide in LFP, which will sacrifice capacity and purity. Meanwhile, the issue of side reactions of cathode electrolyte interface is unresolved still. So the path forward is a synergy of multiple approaches. So something like combining surface coating, doping, and morphological modifications at the cathode. Coming to the challenges, modification strategies, and recent research directions for the anode. So, anode, the performance limitations are primarily due to sluggish lithium ion deintercalation kinetics on the surface. So, the root of the problem is the diminished ionic and electronic conductivities and poor solid electrolyte interface, the SEI layer conductivity, which exacerbates the lithium surface deposition rather than intercalation into the anode. So, the dominant strategies are coating and element doping. So in case of carbon-based anodes, let's take the case of graphite anode, which is a most widely used and conventional anode. It faces severe limitations in low temperature. So uh, nitrogen doping can create branched nitrogen graphitic tubular structures, which will enlarge the interlayer distances and boost conductivity. Another approach is to employ coatings like copper or tin on oxidized graphite, which will reduce the polarization and the charge transfer resistance by facilitating electron transfer. Then graphene anode is another carbon-based anode which is being studied. And in case of graphene, modifications include multi-layer crystalline structures to minimize particle thickness and nitrogen-doped titanium dioxide, titanium nitride, graphene nanocomposite has shown to enhance capacity due to the combined effect of the individual components. Now, carbon nanotubes is another carbon-based anode, which, when combined with porous graphite nanosheets as a composite, has shown to shorten lithium diffusion paths and increase intercalation sites through additional pores, and also it prevents sheet restacking. Now, composites like lithium titanate, silver, carbon nanotube has shown to improve performance by offering abundant lithium insertion sites. And other carbon variants, such as iron doped carbon nanofibers and pre-lithiated hard, soft, and porous carbon, has shown promise through enhanced capacity. Now, looking at titanium based anodes, particularly lithium titanate, it offers excellent thermal stability, low volume change, and high operating voltage, which effectively minimize lithium plating, but it reduces the overall cell voltage. So it totally eliminates the problem of lithium plating and dendrites, which are a serious problem in graphite anode. So though these materials generally have lower conductivity compared to carbon, like titanium and all, surface modifications through carbon coating and doping are employed to mitigate this drawback. So looking at alloying techniques for anode, so silicon-based alloying offer exceptional theoretical capacity. In fact, more than 4,000 milliamp hour per gram, but they suffer from huge volume expansion, leading to mechanical failure, and this is a major problem. So silicon anode and NCA pouch cell has shown higher discharge capacity even at minus 40 degrees Celsius. Coming to volume expansion issues, nanostructuring and porous designs are being explored to accommodate the strain. Similarly, tin and germanium anodes exhibit high capacities, but they degrade due to cyclic mechanical stress. Again, integrating them into composite architectures with carbon matrices can reduce degradation, though these remain in exploratory stages at this point. So the overall takeaways are that graphite-based carbon anodes face lithium plating and dendrite risks at low temperatures due to low operating voltage. Although improvements like coating, doping, and pre-lithiation may help, their performance remains insufficient. Now, titanium-based anodes offer better safety and stability in cold conditions, but they are limited by low energy density. Alloying anodes show great promise due to their high theoretical capacity, but they suffer from severe volume expansion issues, stalling their deployment. So, although non-carbon anodes aren't fully developed yet, they hold strong potential for low temperature applications. Now, let's look at the challenges, strategies, and research directions of the electrolyte. Maybe this is the most critical piece of the puzzle among the battery materials. So, it is a crucial focus area, in fact, even more than electrodes, because as temperature drops, the viscosity of the electrolyte increase and the lithium ion conductivity decrease, and this dramatically limits the diffusion process, posing a greater restriction in the electrolyte than in the electrodes. So the key challenges are increased viscosity and reduced conductivity because at low temperatures the electrolyte thickens and it slows lithium ion mobility. It results in poor wettability and compatibility of the viscous electrolyte. So viscous electrolyte struggles to wet the electrodes and separator, increasing interfacial resistance and if will decrease the efficiency. And it results in a thicker SEI formation. So a dense SEI obstructs lithium ion transportation and desolvation, further impeding the performance. So modification strategy is about finding that optimal electrolyte. So let's look at what is an ideal electrolyte, right? So as we know, it should have low freezing point, high ionic conductivity, low electronic conductivity, low viscosity, stable film forming ability or the SEI formation, wide electrochemical stability window. It should be non-volatile and safe. But such a perfect electrolyte does not exist. And the design of a low temperature electrolyte centers around striking a balance between high dielectric constant, which is important for salt dissociation, and low viscosity, which is important for ionic mobility and reduced charge transfer resistance. And a perfect solvent meeting both criteria is rare. So researchers explore solvent blends and additives um, to optimize the performance. So, for example, ethylene carbonate, which is the most commonly used electrolyte, has high dielectric constant. It has excellent film forming properties, which is all great, but it freezes easily. So, its freezing point is at around 36 degrees Celsius. So, the question is how can we use ethylene carbonate and at the same time bring its freezing point down? So, solvent blends and additives can help in this. So the figure on the right shows SEI layer formation before and after using methyl butyrate as co-solvent at low temperature. So in the after case, the SEI film, which is in gray color, is uniform as opposed to the discontinuous one in the previous case. One strategy at the electrolyte is to add co-solvents with a low freezing point and low viscosity to ethylene carbonate to form a combined solution that performs better at low temperature. One research focuses around using linear carboxylates as co-solvent. So due to their low freezing point and low viscosity, linear carboxylates such as methyl acetate or methyl butyrate are considered co-solvents. And they offer better conductivity and SEI properties, but they are prone to decomposition when the temperature rises. So they work well in low temperature, but they decompose when the temperature rises. And this is a limitation to be addressed. So carbonate-based co-solvents like combination of ethylene carbonate or propylene carbonate and ethyl methyl carbonate and dimethyl carbonate, they offer better stability than carboxylates, but they have higher freezing point than linear carboxylates. So coming to fluorinated solvents, so all fluorinated carboxylate ester-based electrolyte with NCM chemistry has shown to offer greater capacity at around minus 60 degrees Celsius. Similarly, fluorinated carbonate added to highly fluorinated nonpolar solvent offer good capacity even at ultra low temperatures like minus 85 degrees Celsius. So, in addition to common carbonates and carboxylates, several novel solvents also have been investigated. So, isoxazole as a new solvent has shown high dipole moment, freezing point of minus 67 degrees Celsius, and low viscosity. LiDFOB, sulfolane, dimethyl sulfite electrolyte offers better cycling performance, great lithium transport properties, and good SEI formation capability because of the presence of DMS in it. Diox-based electrolyte offer good ionic conductivity at minus 80 degrees Celsius. Nitriles have gained interest, but they have problem of toxicity and poor safety and low compatibility with anode. So um, now, when we talk about lithium salts in electrolyte, their solubility and dissociation are important properties, and they directly affect ionic mobility and SEI formation. An ideal, again, no ideal exists, but an ideal lithium salt should dissolve and dissociate well in the solvent. But equally important is that its anions must remain stable on the electrode surface to avoid unwanted side reactions. So LiPF6, the lithium hexafluorophosphate, is the most widely used lithium salt today. That's because it offers good balance of properties like decent conductivity and SEI forming behavior, but it's not perfect. It tends to decompose into lithium fluoride and hydrogen fluoride. Both are corrosive and it performs poorly at low temperature. Now, the main alternative salts being explored are uh, being explored, but still lithium LiPF6 remains the dominant choice. But one promising strategy is blending. So combining LiPF6 with other salts to enhance the performance of LiPF6 while minimizing its drawbacks. So looking at some of the recent research directions, so LiBF4 salt has smaller anionic radius and stronger binding capacity. It has shown to have lower RCT, but has corrosion and unsatisfactory film forming at low temperature. Now, uh, LiBOB has great film forming capability, but high viscosity and low solubility in carbonate. Dual salt electrolyte like LiBF4 and LiBOB doesn't have enough capacity. LiDFOB combines the advantages of LiBF4 and LiBOB, and it has great outcomes at minus 70 degrees Celsius, but has solubility problems. Now, LiTFSI and LiFSI has desirable thermal stability and low RCT, but has corrosion problems. So another approach is to have high concentration electrolyte and localized high concentration electrolyte. So the idea is to add an inert solvent to dilute the high concentration electrolyte to form a localized high concentration electrolyte. This reduce viscosity, so which will in turn improve lithium ion transport. So dichloromethane as a diluent in LiTFSI, eth ethylene, ethyl acetate, and chloromethane electrolyte has low viscosity and low freezing point of minus 95 degrees Celsius, so and has great conductivity at low temperature, even at minus 70 degrees Celsius. So coming to the strategy of adding additives to electrolytes. So additives change the composition and structure of SEI during cycling by inhibiting the growth of the detrimental SEI and increasing the ionic conductivity. So two of the most widely used additives are fluoroethylene carbonate, added to propylene carbonate-based electrolytes, and vinyl, vinylene carbonate, added to ethylene carbonate-based electrolytes. So fluorinated additives like FeC plus Fi into LiPF6 EC-DMC electrolyte for graphite lithium-ion battery has shown higher capacity at minus 20 degrees Celsius. Some lithium salts have also been employed as additives, like because of their better film forming performance and stable SEI. So, for example, the lithium difluorobis oxalatophosphate, or LiDFBOP. So the takeaways are compared with electrode materials, the modification of electrolyte is a more efficient and cost-effective strategy to tune the low temperature performance of lithium-ion batteries. So the key to unlocking low temperature performance is in finding that electrolyte which has high conductivity, low viscosity, weak solvation structure, and low freezing point. So the path forward is most likely is using a co-solvent. So fluorinated solvents or novel solvents are being explored right now in research. So the final takeaways on the material strategy is that cathode materials, the techniques used are surface coating, particle modification, and element doping. And the current focus is in optimization and modification of common materials such as LNMO or LFP, and lithium cobalt oxide, but they all suffer from moderate side reactions. At anode, materials coating, particle modification, and element doping and pre-lithiation are the most you, explored strategies. An attractive anode candidate is the titanium-based materials, although graphite has better comprehensive properties. So titanium um, is promising because they can handle lithium well with little swelling, and they have higher voltage, which helps in preventing the dangerous lithium plating. And this also, but it has a downside of lower energy density, but it completely eliminates the safety issue of graphite anodes. And electrolyte, low freezing point, low viscosity cold solvents, solvent fluorination, blended salt electrolytes, high concentration electrolytes, and appropriate additives are the dominant strategies. So researchers have made huge advancements in designing a better anode or better cathode or better electrolyte individually. And we looked at some such promising research directions. But the catch is that putting these parts together to create a safe, reliable product is a challenge. Because most of these potential candidates, when put together, they trigger side reactions, they struggle in low temperature, and they have hidden safety risks that we haven't fully tested yet. So, a battery that works flawlessly at minus 20 degrees Celsius and won't overheat or result in safety risks and is cost effective is a real breakthrough, and we are not there yet. Now, here is a recent paper which was published just a week ago by a couple of researchers from University of Michigan. So they have employed a modified manufacturing process to achieve a breakthrough performance at low temperature. So the goal was to avoid this auxiliary heating systems that that are bulky and they consume additional energy and they take time to heat before charging and are not feasible in many portable applications even. So their condition was to achieve fast charging of more than 3C, low temperature operation of less than 5 degrees Celsius, and high energy density thick electrodes, which is what most of the EV batteries are. So their approach was to use interface engineering and 3D architecture. So um, they performed interface engineering to improve the mass transport and interfacial performance um, by surface coating with a glassy material made of lithium borate carbonate. So using that material, they created an artificial SEI layer using this process called ALD, which is atomic layer deposition. And they created a 20 nanometer thick SEI layer, and they used 3D architectured graphite anode. And this was done using the later patterning process. So, which will improve, will better the utilization of active material particles deeper inside, deeper within the electrode. So the results are, that now this is very promising. So 6C fast charging of minus 10 degrees Celsius without lithium plating, and they achieved, they they they, they found that it retains 97% of the capacity even after being fast charged 100 times at very cold temperature. So this is very promising, but if you look at the process used, which is ALD, it excels in lab for precision engineering of SEI layers, but it's also very expensive and it's not commercially viable at this moment. So this is probably may not be a cost-effective solution. Now, overall, as scientists are exploring research, material challenges, external preheating strategies are the most viable solution at this point. So external heating methods based on battery thermal management systems use these devices from the outside to transfer heat through heat transfer mediums such as air, liquid, or phase change material, or even thermal plates or films. So the key methods are air-based preheating, which use air as the medium. It is simple and low cost, but has poor thermal efficiency and uneven temperature distribution. Earlier EV like Prius used it, but today it's rarely used. Liquid-based preheating is the most dominant strategy today because of its efficiency and uniform temperature control. It is combined with coolant loops with energy intensive positive temperature coefficient heaters, as in Volkswagen ID3, or compact high voltage coolant heaters. So advanced setups like Tesla's Octovalve integrates this heat pump to recycle waste heat and optimize energy use, and also it preserves range. Now, phase change material leverage materials that absorb or release heat. This is effective in lab, but it's not mainstream. Then electrothermal element preheating incorporates resistive plates or Peltier devices, but they also suffer from low efficiency, like in the case of Nissan Leaf, and they have the risk of overheating. Hybrid preheating is a combination of multiple strategies from these. So, in conclusion, liquid-based preheating is, especially those combining PTC heaters or heat pumps like in Tesla, are preferred because they balance safety, efficiency, and reliability. Hybrid approach is also has high potential, but it requires a real-world validation. So another practical strategy is mixed chemistry battery pack. So this is very promising in my opinion, and the idea is to combine different battery chemistries to leverage their individual strengths. So something like a cold weather assist system, which will combine the regular batteries like LFP or NMC with LTO or some special batteries, which works well in low temperature. So as in this case, LTO can operate well down to minus 30 degrees Celsius, and it has better fast charging and discharging ability and long cycle life, and better low temperature performance. But then it is expensive and it has low energy density. And also, if we look at the challenges of the BMS, it needs a complex BMS which uses a smart thermal management strategy, which needs some temperature aware switching logic. So in that case, LTO cells activate first, supplying power to heating elements, preconditioning secondary cells. And once it has heated up and reached above 0 degrees Celsius, it can switch to NCM or LFP, the regular battery. But then there is a question of like how do we meet the range, power, and packaging and space constraints, right? Because all these different batteries have different energy density and chemistries, and they may need different heating methods or cooling methods, um, and what will be the ideal ratio between this regular battery and this cold weather special battery, right? So because it will affect the packaging, also space constraints in the vehicle. Um, and the emerging chemistries are, this sodium ion. It is inferior to LTO. So Cattle already launched a sodium ion battery just recently, and it's expected to get better over time. BYD is saying that it is expecting to begin demonstration use of all solid state batteries by 2027. So solid state batteries are going to be a huge breakthrough. Not only that it'll address the issue of low temperature operation, but it'll also address many other limitations that plague the lithium ion batteries today. So that's very, very high potential, but it's it's not there yet. Now, yet another approach is using hybrid energy storage system. So one approach is combining lithium-ion battery with supercapacitor. So supercapacitor or ultra capacitor can operate efficiently even at minus 40 degrees Celsius. They offer high power density, meaning they can deliver quick bursts of power or absorb energy for regen braking. And a smart power management system can dynamically shift the load between battery and supercapacitor based on demand, temperature, and the state of charge. It can provide immediate power even when the battery is cold. Another approach is using lithium ion battery with range extender. So, range extenders are miniaturized, efficiency focused, small ICE engines, or it can be fuel cells or thermoelectric generators. And an example of this small ICE engine range extender is the BMW i3 REX. So they offer extra energy and preheating for battery, and this acts as a safety net. It improves the charge safety and range in cold, and it compensates for energy loss in EVs. And in fact, it also is is great for solving another issue of electric vehicles like range anxiety, right? So this always acts as a backup to batteries. But the criticism is that it adds emissions, um, very low, but it still adds emissions, and it increases complexity. So it's probably less ideal for pure EVs, but it's still a very practical and viable solution. So uh, benefit is that it overcomes the cold weather weakness of individual technologies, which is the batteries, um, and it enhance reliability and performance. So it's like three teamwork, so which makes things happen. Right? So the final takeaway is that cold weather challenges need a versatile solution. So no single approach is enough, but a combination of multiple approaches would be the effective solution. So researchers are working on material innovations, and they're in the making, but they're not there yet. External thermal management is the most widely used strategy today, and we saw that it results in delays and inefficiency, and it also poses reliability issues. Now, mixed chemistry battery is a promising solution, in my opinion. And HESS, the hybrid energy storage system, is a solid solution as well, except for a little bit of emission, as in the case of range extenders. So that concludes this presentation. Thank you. And if any questions